This video covers magnetic fields. Magnetism is very similar to electricity. Magnets have two poles, north and a south. These like poles repel and unlike poles attract. Magnetic fields, however, form continuous loops. That means that outside of a bar magnet, the magnetic field runs from north to south, whereas inside of a bar magnet, the magnetic field runs from south to north, as you can see from this picture down here. Our magnetic field is going to be represented by a capital B, and we're going to have a new unit of Tesla. Also, magnetic field is a vector, so we're going to see that how it plays into our calculations later. If you've ever seen a compass, you know that it has a needle, and on one side of the needle, it's either colored and tells you that it's pointing to north. Well, this is to get to the geographic North Pole. That's actually the magnetic South Pole. So inside of our Earth, on the North Pole is actually the south part of the magnet, and at the South Pole we actually have the north part of the magnet. Magnetic fields can be created by charges that are moving. So if we have a wire that has a current running through it, it actually generates a magnetic field. And we're going to be able to determine the direction of the magnetic field with a new right-hand rule. Now this right-hand rule is a curling rule. That means that your thumb is going to point in the direction of the moving charges or the current, and your fingers are going to curl around the wire, and the direction that your fingers point are the direction of the magnetic field lines, like you see in this picture. Again, by default, current is we consider as positive charges that move throughout our circuit. So that means you're going to be using your right hand. Now later on we are going to see a left hand rule, but we'll talk about that when we get to it. Since our pictures can be three-dimensional, we need to reintroduce our coordinate system. Remember that x and y lie on the plane of the page, whereas z comes in and out of the page. So remember that x's are going to represent going into the page and dots are going to represent coming out of the page. And we said a good way to remember this is like an arrow. The arrow coming towards you, you're going to see a dot. An arrow moving away from you, you're going to see an X, which is the cross of the feathers. So here's an example where you have one wire and you have your thumb going to the right. Again, on one side of the wire, the magnetic field is coming out of the page. Again, it's curling around. And on the other side of the wire, it's going into the page. Again, you're going to represent it by dots coming out and crosses going in. Again, going into the page is going to represent it by negative z. And then coming out of the page is going to be represented by a positive z. Now here's a slightly different example. What you're seeing here is a dot that shows the direction of the current, not the magnetic field. So if the current is coming out at you, that means your thumb is pointing toward you. And the direction of your fingers are going counterclockwise. In this example, you have the cross that's showing the, again, current, not the magnetic field. So if the current's going into the page, then your hand is awkwardly flipped and your fingers are going in the clockwise direction. Now we can calculate the strength of that magnetic field using this new equation. Again, B is magnetic field with units of Tesla. Mu naught is a constant, which is 4 pi times 10 to the negative 7. I is current in unit of amps. And R, again, is distance away from the center of the wire. Now, because mu naught, 2, and pi are all constants, it's also easier to simplify all of those constants to just 1, which is 2 times 10 to the negative 7. Now, you may also find K prime in your constant sheet. K prime is 1 times 10 to the negative 7, and this is the permeability of free space to a magnetic field. Okay, very similar to K in electric fields. So 2 times that value can also replace 2 times 10 to the negative 7. Here we have a wire with a current of 1.8 amps. Point P is located 12 millimeters from the wire, and we're asked to determine the magnitude of the magnetic field. Again, we can use our new equation where we said mu naught over 2 pi is 2 times 10 to the negative 7. Our current is 1.8 amps, and our distance away from the center of our wire is 12 millimeters, which is 0.012 meters. Which just gives you 3 times 10 to the negative 5 Tesla. Now, to determine the direction, again, you put your thumb in the direction of the current, which again is going to the left in this case. Your fingers curl around the wire. So at point P, it is coming out of the page. If we were looking at a point over here, it would be going into the page at this part. Here we actually have 2 wires. Now remember that magnetic field is a vector, so we simply need to find the magnetic field of one, find the magnetic field of the other, and if they're in the same direction, add, and if they're in opposite direction, subtract. So, to find the one in blue, we're going to say B is equal to 2 times 10 to the negative 7. Our current for our blue wire is 2 amps. The distance away from that wire is 1 meter. So this is simply 4 times 10 to the negative 7. For our red wire, the magnetic field is 4 times 10 to the negative 7. Now, to determine direction, again, our thumb goes down or down and to the right. So our magnetic field is going to come out of the page for the blue wire. And then if we point our thumb in the direction of the red wire, it also comes out of the page. So because they're both pointing in the same direction, we're going to add them. So our total is simply 8 times 10 to the negative 7. Again, it's coming out of the page, which is positive Z. Here we're looking at 2 wires. Again, both of these wires represent currents that are coming either toward you or away from you. So starting with the blue wire, this blue wire is going away from you, so that means that this one produces a magnetic field going clockwise. So at the origin, the magnetic field is tangent to that circle. So to find the strength of that magnetic field, we simply times our constant times our current divided by the distance away. It says that they are both 1 meter from the origin, so that's just 4 times 10 to the negative 7. Again, Tesla. For the red wire, it is going towards you, so it creates a magnetic field that is counterclockwise. So that means at the origin, the line that is tangent to it would be going straight down. So to find the strength of that magnetic field, it is 2 times 10 to the negative 7 times my current, 1, times my distance, 2. Actually, my distance is also 1. So that's just 2 times 10 to the negative 7 Tesla. Again, because they're vectors, you have to add them vectorially. That means that it's going to, my vector resultant is going to be pointing out somewhere in this direction. So, to find that, Pythagorean theorem. And we get 4.47 times 10 to the negative 7 Tesla. Now again, because it's a vector, it needs both magnitude and direction. So this only gives me my magnitude. Inverse tangent gives me direction. So opposite is going to be 2 times 10 to the negative 7. Adjacent is going to be, again, I'm solving for this angle right here. Adjacent is 4 times 10 to the negative 7. So my angle is 26.6 degrees. But we know that all angles are measured from the 0 all the way to that point. So that's 26.6 times 180 to give us a final angle of 206.6 degrees. 207, it's fine.